Hello and welcome back to Math 1324. We're going to take a look at systems of linear equations and augmented matrices. This is the second section in chapter 4, which was systems of linear equations and matrices. Okay, let's go take a look at an introduction to matrices, some definitions. A matrix is a rectangular array of numbers written in brackets. So the first definition is matrix. A matrix, a rectangular array of numbers written in brackets. Each number in a matrix is called an element of the matrix. If a matrix has m rows, and remember that rows go this way, and n columns, then it's called an m by n matrix. So you always list the number of rows first and the number of columns second. The expression m by n is called the size of the matrix. Okay, a matrix with n rows and n columns is called a square matrix of order n. You could also say it's an n by n matrix. A matrix with only one column is called a column matrix. And a matrix with only one row, guess what that's called? It's called a row matrix. So an example of that would be like a row matrix would be maybe 1, 2, 4. That's a row matrix. It's a 1 by 3 matrix. Do you see that there's 3 columns? The first element in the first row, the first column, is a 1. That's an element. Each one of those are entries are elements. Okay, keep going. The position of an element in a matrix is given by the row and column containing the matrix. So again, this would be element A11. This one would be element A12. First row, second column. So let's go fill in the blank. The position of an element in a matrix is given by the row and column containing the element, denoted by using a double subscript notation. A double subscript notation. The elements A11, A22, A33, those make up what's called the principal diagonal of the matrix. The principal diagonal. Let's look at some specific examples of matrices. Okay, matrix A. The size of matrix A, there are 2 rows and 3 columns. So it's a 2 by 3 matrix. What about matrix B? Matrix B has 3 rows, so it's going to be a 3 by and only 2 columns. So it's a 3 by 2 matrix. Looking at matrix C, there are 2 rows and 2 columns. So it's a 2 by 2 matrix, or we can say that it's a square matrix of order 2. So why are we talking about matrices? Let's go look at the relationship between systems of linear equations and matrices. If you have a linear system, so 2 equations, you've got this number times x1 plus this number times x2 equals a number. And then you've got another number times x1 plus a number times x2 equals this number. I think in the last section we wrote it like this: ax plus by equals c, and then, nope, that's a d, not a c. and then dx plus ey equals f. That's how we wrote a generic system with two equations, two unknowns in the last section. Okay, here our variables are x1 and x2. We say that it can be written as an augmented matrix in the following way. We're going to put, let me find the highlighter. We're just going to put the numbers out front of the variables in the matrix here. A11, A12, A21, and A22. And then we're going to put the numbers on the right-hand side of the equal sign over here. So K1, K2. Okay, some things to point out. It's an augmented matrix. Do you see where the equal sign is? In your matrix, you're just going to put this vertical bar there. Okay, we can also differentiate what's called the coefficient matrix. The coefficient matrix, that's just this side. So it's going to be A11, A12, A21, and A22. And then you have what's called the constant matrix. And it's just the column matrix on the right-hand side of the equal sign, or in the augmented matrix, it would appear on the right-hand side of the vertical bar. So the constant matrix is K1, K2. Okay, so there's three types of matrices going on here that you get from what's called the linear system up here. You get the augmented matrix, which puts all of the numbers in a matrix, and you're going to put a big vertical bar where you see the equal sign. If you just talk about the numbers to the left of that big bar, that's called the coefficient matrix. And if you just talk about the numbers to the right of that bar, that's called the constant matrix. All right, so let's go look at some examples. Here are two examples that say to write the following system as an augmented matrix. So let's go look at number one. I have two equations, so I'm going to have two rows, and I'm going to remind myself I want to put a vertical bar there. So here comes the augmented matrix. It's in the right form, 3x plus 4y equals 1. So my numbers are going to be 3, 4, here's my bar, and 1. My second equation is x minus 2y equals 7. The number that you don't see that's understood there in front of that x, what is it? It's a 1. So I have 1, negative 2, and then to the right of the bar is going to be 7. Now you go try number 2. Writing the augmented matrix for number 2, I'm going to remind myself, here's the bar. I'm going to have 2, 1, the bar, and 6. The second equation gives me 1, negative 1, negative 3. Okay, now we're going to go backwards. I'm going to give you the augmented matrix. Can you write the system of linear equations? So for number 1, here's the system. This row, I'm going to have 1x plus 5y, and remember that bar means equals 4. My second equation will be 3x minus 2y equals negative 12. Now you go try number 2. For number 2, you get the system 1x, or just x, plus 0y. But what is 0 times y? Isn't that just 0? So you don't need to write anything. You get x equals 2. In that second equation, you get 0x plus 1y, so y equals -1. I wonder if matrices of this form, where you have 1, 0, 0, 1, I wonder if that's a special type of matrix. Now we're going to talk about row equivalent matrices. There's a theorem. The theorem is about operations that produce what are called row equivalent matrices. An augmented matrix is transformed into a row equivalent matrix by performing any of the following row operations. Okay, the row operations are, here are the rules that you can do. You have to play by these rules. You can swap any two rows. So two rows are interchanged. So something that you might see would be like row 1 is swapped with row 2. So you can swap rows. The second thing you can do to produce a row equivalent matrix, a row is multiplied by a non-zero constant. So if I wanted to multiply row 1 by the number 3 and then make that into my new row 1, I can do that. And just a side note, that's because of the multiplication property of equality. But you can multiply a row by a non-zero constant. And then the third thing says that a constant multiple of one row is added to another row. So let's say we multiplied row 1 by 3, and then we added that to row 2. We can insert that to become our new row 2. Let's go look at some examples. It says, perform the given row operation. A couple of things to point out. Do you see this little squiggly here? That squiggly means that it's equivalent to. So we're going to write, here's the matrix, and we're going to write an equivalent matrix. All right, our row operation says that it wants us to do, what does this mean? Swap row 1 and row 2. So my row 1, 630, becomes my row 2. My row 2, 1, -2, -12, becomes my row 1. That's all you do when you're swapping rows. You just switch places with the rows. You go do number 2. All right. It's wanting you to swap row 1 and row 3. Does it say anything about row 2? The answer is no. So this row 2, oops, here in row, that's not going to let me do that. Everything in row 2 stays the same. I'm just going to rewrite row 2. 6, 1, 2, 5. Okay, the directions tell me to swap row 1 and row 3. My row 1, 3, 6, -8, -7, becomes my row 3. 3, 6, -8, -7. Now my row 3 becomes row 1. 1, -2, 7, 8. These two matrices are what are called row equivalent matrices. Let's go look at number 3. Number 3 wants us to do 3 times row 1 and make that my new row 1. It doesn't say anything about row 2. So I'm going to keep row 2 the same. 6, 3, -12. All right. It wants me to take 3 times row 1 and become a new row 1. I'm going to put a 3 out here around row 1. And now I'm going to distribute that 3 to everybody. 3 times -2 is -6. 3 times 4 is 12. 3 times -6 is -18. All right, the last row operation. You're going to do a multiple of one row, add it to another row, and then replace the second row. All right. Do you see over here, it says to replace as your new row 2. So my row 1 doesn't change. I'm going to go put 1, 3, 6. All right, the row operations. Say to do -2 times row 1. First thing I'm going to do, -2 times row 1. What am I going to get? -2, 3, 6. No, sorry. -2, -6, -12. I've got to distribute. All right. I did -2 times row 1. I want to add that to row 2. 2, 4, -1. When I add those, what do I get? 0, -2, -13. This becomes my new row 2. So I get 0, -2, -13. If you need to go do that again, please do. Our next section in the notes, solving linear systems using augmented matrix methods. The goal is to use row operations to try to transform the augmented matrix into the following form, where m and n are real numbers. We saw this on the bottom of another page previously. This would mean that 1x equals m, and then 1y equals n. So the solution would be the ordered pair m, n. This would be the solution to that system, right? All right, so let's go do an example. Solve the following system using augmented matrix methods. So they give you the system. First thing you want to do is write the augmented matrix. You're going to write 2, -1, -7. Then you're going to write, look at the second equation. What are the numbers that are out front? You're going to write 1, 2, 4. Your next step is to get a 1 here in the A11 position. Okay, we could accomplish that by interchanging these two rows. So the row operation will look like this. Row 1 swapped with row 2. After we do that, row 1 becomes row 2, and row 2 becomes row 1. All right, we now have, our 1 in the top left position. That's good. Our next goal is to concentrate on the number underneath that 1. We're going to concentrate here. We want to get a 0 there. The only thing we have to use is this number right here. So I'm going to add a constant multiple of what to row 1, of row 1 to row 2? And right now I'm going to give it to you. You're going to do -2 times row 1 and add that to row 2 and make it your new row 2. Because we're changing row 2, I'm going to leave row 1 alone. All right, I want to do -2 times row 1. So I'm going to put a big set of parentheses here and do -2 out front. What would I get? -2, -4, -8. I want to add that to row 2. 2, -1, -7. If I add those two rows, I get 0, -5, -15. That's my new row 2. To summarize, what have we accomplished? We got a 1 in the top left, then we went after getting a 0 in the bottom left. Next, from this matrix, we want to get a 1 right here. We're going to accomplish that by multiplying row 2 by -1/5 and making that my new row 2. So this step, it does not say to touch row 1, so I'm going to leave row 1 alone. But I want to multiply row 2 by -1/5. -1/5 times 0, -1/5 times -5, -1/5 times -15. All right, let's recap. I got a 1 here, then a 0 here, then a 1 here. My last step, I've got to turn that into a 0. To do that, I'm going to give you the row operation for now, right here. To do that, I need to multiply this row by -2 and add it to row 1. If I multiply this row by -2 and add it to row 1, am I going to do anything to row 2? No, I'm only changing row 1. So I'm going to write row 2 down again. Okay, now I got to do -2 times row 2, which is going to be 0, -2, -6. If I add that to row 1, I get 1, 0, -2. All right. What is my solution to this equation? My solution says, or my matrix says, x equals -2 and y equals 3. You can write it like that, or you can give me the ordered pair -2, comma 3. Let's go do this process again. Solve the following system using augmented matrix methods. The system is 3x plus 4y equals 1, x minus 2y equals 7. The augmented matrix will be 3, 4, 1, 1, -2, 7. I want a 1 up in the top left corner. I can accomplish that by swapping row 1 and row 2. I get 1, -2, 7, 3, 4, 1. Now my attention will be here. I want to get a 0 there. I'm going to do that by multiplying this 1 by -3 and adding it to the 3. So my row operation is -3 times row 1 plus row 2 becomes my new row 2. I'm not going to change row 1, but I am going to take, and I'm going to do that with a different color. I'm going to take this row 1 and multiply it by -3. So what is that? -3, 6, -21. And I want to add that to 3, 4, 1. I get 0, 10, -20. So my row 2 is going to be 0, 10, -20. Good. We've got a 1, we've got a 0. We now need a 1 here, so we're going to multiply row 2 by 1/10. All right, 1/10 times row 2 becomes new row 2. So 1/10 is going to go here. I'm not going to change row 1. It stays 1, -2, 7. 1/10 times 0, 1/10 times 10, 1/10 times -20. One more step. I've got a 1, a 0, a 1. Now I need to get a 0 here. I need to multiply this 1 by 2 and add it to the row 1. So I'm going to get a different color. 2 times row 2 plus row 1 becomes row 1. I'm going to multiply this one by 2. I'm not changing row 2. 0, 1, -2. That stays the same. Now I'm going to do this part of my row operation. 2 times 0, 2 times 1, 2 times -2, and I want to add that to row 1, 1, -2, 7. I get 1, 0, 3. That's my new row 1. Okay, what's my solution to this system? My solution is x equals 3, y equals -2. It's okay to write the ordered pair 3, -2 as well. All right, the last part of these notes, the summary. You're going to notice that we're going to talk about this later too in the next section. But the possible final matrix forms for a system of 2 linear equations and 2 variables, you have to have one of the 3 situations. This is the situation we've seen in the previous 2 examples. That tells you that you have one solution. In other words, if you remember from last section, it's a consistent system with independent equations. You're going to see that x equals m and y equals n. Consistent system with independent equations, so you have one solution. Your matrix could be of this form. Something I want you to notice, do you see this row of zeros down here at the bottom? You have a row of all zeros. That is what's called a consistent system with dependent equations, indicating that there are infinitely many solutions. And that's because you have a row of all zeros. Okay, the third situation, you've got 0 equals p. So 0 equals a number that's not 0. Okay, that's going to give you an inconsistent system, and you're going to say that there is no solution. So, recap, if you have this identity matrix 1, 0, 0, 1, you have one solution, and your solution is the ordered pair m, n. If you have all zeros, you're going to have infinitely many solutions, And we'll talk about how to write those solutions in a minute. And then if you have 0 equals a number other than 0, your answer is no solution. All right, that's it. If you will go log in and complete your homework for this section. We'll see you again next time.